The economics of modern attrition warfare have subverted a fundamental assumption of Western military doctrine, that technological superiority guarantees long-term strategic dominance. For decades, the United States and its allies operated under the premise that high-end, precision-engineered platforms could decisively neutralize massed, low-cost threats. However, the systematic deployment of low-cost loitering munitions and tactical ballistic missiles in contemporary conflicts has inverted this dynamic. Air defense is no longer strictly a question of kinetic interception efficiency. It has transformed into a brutal war of economic and industrial attrition. When a single interceptor missile costs orders of magnitude more than the incoming threat, the defender faces a mathematical certainty of exhaustion, regardless of the system's tactical success rate.
At the center of this paradigm shift sits the MIM-104 Patriot missile system, specifically its latest iteration, the Patriot Advanced Capability 3 Missile Segment Enhancement, PAC-3 MSE. Nominally priced at approximately $4 million per interceptor, the PAC-3 MSE represents the pinnacle of terminal hit-to-kill technology, engineered to neutralize high-speed ballistic and air-breathing threats. Yet, when deployed against mass-produced, low-altitude drones or older Soviet-era cruise missiles, the financial asymmetry becomes unsustainable. A defense architecture that expends millions of dollars to destroy a threat costing less than a high-end consumer vehicle introduces a profound structural vulnerability. This vulnerability is not a flaw in the Patriot's radar or guidance systems, but rather a systemic misalignment between military capability and economic reality. To understand why this is a critical vulnerability for the United States, one must look at the physical limitations of Western defense manufacturing. The contemporary American defense industrial base is optimized for low-rate, high-margin production of highly sophisticated systems, a legacy of post-Cold War consolidation. This framework works efficiently during peacetime or localized asymmetric interventions, but it fails under the demands of prolonged state-on-state conflict. When regional conflicts erupt simultaneously across multiple theaters, the demand for interceptor replenishments rapidly outpaces factory throughput. The United States now finds itself in a position where its strategic reserves are being drawn down faster than its industrial base can replenish them, creating a dangerous window of vulnerability in secondary theaters.
From an analytical perspective, evaluating the Patriot system requires stripping away the political rhetoric and focusing strictly on the hard metrics of operational data and manufacturing capacities. The system's performance in combat zones has demonstrated remarkable technical capabilities, particularly against complex targets, but tactical efficacy cannot be divorced from industrial reality. An air defense system with a 95% interception rate is still a strategic failure if the defender runs out of missiles, while the attacker still possesses thousands of munitions. Therefore, examining the Patriot paradox requires an objective assessment of three interconnected variables: the mechanics of the target threat profile, the current state of US domestic production, and the geopolitical trade-offs governing global deployment. The technical sophistry of the PAC-3 MSE is undeniable, utilizing a solid propellant rocket motor and active radar seeker to achieve hit-to-kill kinetic interception. Unlike older variants that relied on proximity fuse fragmentation warheads, the PAC-3 MSE physically collides with incoming targets, destroying them through sheer kinetic energy transference. This approach is highly effective against tactical ballistic missiles carrying weapons of mass destruction, as it ensures the complete obliteration of the warhead. The system's AN/MPQ-65 radar and advanced engagement control stations provide unparalleled tracking and guidance capability in contested electromagnetic environments. Yet this extreme engineering sophistication is precisely what hinders the system's scalability when mass production becomes an urgent geopolitical necessity. The production bottleneck for the PAC-3 MSE is primarily concentrated within Lockheed Martin's manufacturing facilities, notably its Missiles and Fire Control Division in Camden, Arkansas. Despite concerted efforts by the Department of Defense to surge production, expanding the manufacturing capacity of a highly complex guided missile is a slow, capital-intensive process. As of recent operational quarters, the production rate for PAC-3 MSE interceptors has crawled from roughly 500 units per year toward an estimated target of 650 units annually, with plans to scale to 1,000 units by 2027. However, when multiple global flashpoints are consuming hundreds of interceptors per quarter, an annual production rate of 650 missiles creates a severe structural deficit that cannot be bridged by short-term policy adjustments. This manufacturing constraint is further exacerbated by deep-seated vulnerabilities within the lower-tier defense supply chain. A guided missile like the Patriot is not built in a vacuum. It requires a vast network of sub-tier suppliers providing critical components, including solid rocket motors, advanced semiconductors, traveling wave tubes, and specialized raw materials. Many of these sub-tier suppliers operate as single-source monopolies within the defense sector, meaning a disruption at a single factory can stall the entire assembly line. The defense industry's reliance on just-in-time logistics, a practice adopted from civilian manufacturing to reduce overhead costs, has left it entirely unprepared for the raw material shortages and labor constraints characteristic of a globalized security crisis. The economic math becomes even more troubling when analyzing the cost structure of the threats the Patriot is tasked with intercepting. In modern asymmetric engagements, state and non-state actors routinely deploy long-range loitering munitions, such as the Shahed series, which carry an estimated production cost of $20,000 to $40,000 per unit. When a defense network fires a pair of PAC-3 MSE interceptors to guarantee the destruction of a single loitering munition, a standard operational procedure to mitigate the risk of leakage, the expenditure ratio stands at roughly 400 to 1 against the defender. Even when factoring in the value of the infrastructure being protected, this level of economic asymmetry inevitably drains the national treasury and stockpiles of the defending coalition over an extended timeline. To illustrate this dynamic visually, we can examine the stark contrast between the financial and temporal costs of production for attackers versus defenders. Furthermore, the operational footprint of a Patriot battery limits its strategic flexibility and increases its vulnerability to saturation attacks. A single Patriot battery consists of a radar set, an engagement control station, a power generation plant, and up to 8 launching stations, requiring significant logistical support and a large complement of trained personnel to operate. Because the radar system must emit high-powered electromagnetic signals to track targets, it acts as a beacon for enemy electronic intelligence and anti-radiation missiles. Sophisticated adversaries utilize multi-axis layered attacks, sending waves of cheap drones to force the Patriot radar to activate and exhaust its ready-to-fire missiles before launching high-speed ballistic or cruise missiles to strike the defenseless battery. This tactic of deliberate air defense saturation has been observed with increasing frequency in modern conflict theaters. Attackers intentionally construct strike packages that mix low-end decoys, unguided rockets, slow-moving drones, and high-speed missiles, explicitly designed to overwhelm the processing capacity of the defense system's computer architecture and the physical capacity of its launchers. The defender is forced into a continuous sequence of split-second decisions: ignore a target and risk catastrophic infrastructure failure, or engage the target and deplete a finite, irreplaceable interceptor asset. In a high-intensity environment, the psychological and operational pressure to engage everything frequently leads to rapid magazine depletion, leaving critical nodes exposed to subsequent waves of attack. The strategic dilemma is magnified when evaluating the protection of critical energy infrastructure, an area of particular interest for global economic stability. Power grids, oil refineries, LNG terminals, and deep-water ports are large, static targets that are highly vulnerable to kinetic disruption. A single successful strike on a critical oil processing facility, such as the 2019 drone and cruise missile attacks on Saudi Aramco's Abqaiq and Khurais facilities, can instantly remove millions of barrels of oil per day from the global market, triggering massive price spikes and inflationary pressures. Governments are therefore compelled to station their limited Patriot batteries around these economic assets, pulling vital air defense umbrellas away from forward-deployed military units and population centers. This trade-off creates a fragmented security architecture, where military commanders and civilian leaders must compete for the same scarce defensive resources. If a state prioritizes the protection of its civilian energy grid to maintain domestic stability and economic viability, its forward military bases and logistical hubs are left vulnerable to air interdiction. Conversely, if those air defense assets are deployed to the front lines to protect military maneuvers, the domestic industrial base becomes a soft target for strategic bombing campaigns. This systemic scarcity means that the deployment of a Patriot battery is no longer a purely tactical decision, but a high-stakes macroeconomic gamble with immediate geopolitical ramifications. The geopolitical consequences of this scarcity are currently being felt most acutely within the United States Indo-Pacific Command, or Indo-PACOM. The primary security challenge in this theater is the People's Liberation Army, or PLA, of China, which has spent the past 3 decades building the world's most extensive and diverse inventory of conventional ballistic and cruise missiles. The PLA's anti-access area denial strategy is specifically engineered to target American forward bases in Japan, South Korea, and Guam with massed missile salvos designed to overwhelm existing air defenses. For Washington, every Patriot battery or interceptor diverted to maintain security in Europe or the Middle East directly degrades the deterrence posture required to prevent a cross-strait conflict in Asia. American strategic planners are acutely aware that a conflict in the Indo-Pacific would consume air defense munitions at a rate that would make current global consumption look modest by comparison. War games conducted by prominent Washington think tanks consistently reveal that the United States would exhaust its global stockpiles of precision-guided air defense and anti-ship munitions within the first 2 weeks of a high-intensity conflict over Taiwan. Once these advanced interceptors are spent, forward-deployed U.S. forces would be left exposed to subsequent waves of land attack cruise missiles and anti-ship ballistic missiles, severely limiting the operational freedom of U.S. carrier strike groups and land-based air wings. The industrial base's inability to rapidly surge production under absolute wartime conditions remains the single greatest vulnerability in Western conventional deterrence. To address these compounding challenges, the U.S. Department of Defense has begun exploring alternative defense architectures, though none offer an immediate or painless resolution. One approach involves the integration of lower-cost kinetic interceptors, such as the National Advanced Surface-to-Air Missile System, NASAMS, or the Common Anti-Air Assembly, CAM, into a broader, layered IAMD network. These systems utilize smaller, less expensive missiles that can be produced in larger quantities, allowing them to handle low-tier threats, while reserving the expensive Patriot PAC-3 MSE for high-end ballistic targets. However, integrating disparate weapon systems across allied nations requires complex software synchronization and secure data-sharing networks, which face significant bureaucratic and technical hurdles. Another avenue of intense research and development is directed toward non-kinetic directed energy weapons, specifically high-energy lasers and high-power microwave or HPM systems. These technologies offer a theoretically infinite magazine depth and an incredibly low cost per shot, measured in dollars rather than millions of dollars, making them the ideal conceptual solution to the low-cost drone problem. A single HPM system could instantly neutralize an entire swarm of loitering munitions by frying their internal electronics, completely neutralizing the attacker's economic advantage. Nevertheless, directed energy weapons remain largely stuck in the prototyping and limited field testing phases, hampered by atmospheric attenuation, power generation constraints, and thermal management issues that limit their operational deployment on a meaningful scale. Consequently, for the immediate and medium-term future, the international security architecture will remain heavily dependent on traditional, kinetic missile defense systems like the Patriot. This reality forces a critical re-examination of Allied defense procurement and industrial strategy. The post-Cold War assumption that Western nations could rely on a consolidated, highly specialized, and lean defense industry must be replaced by a model that prioritizes redundancy, manufacturing capacity, and mass production. For the United States, this means investing heavily in domestic factory automation, building deep strategic stockpiles of long-lead subcomponents, and subsidizing the expansion of lower-tier manufacturing suppliers to eliminate single points of failure. Furthermore, Washington must increasingly rely on international co-production agreements to distribute the industrial burden among its capable allies. A prime example of this strategy is the recently initiated plan to co-produce Patriot interceptors in Japan under license by Mitsubishi Heavy Industries, alongside efforts to establish European production hubs for the guidance-enhanced missile PAC-3 MSE variant. By leveraging the advanced industrial capacity of allies in Asia and Europe, the United States can expand global manufacturing throughput and create regional replenishment hubs that reduce the strain on domestic facilities. However, these co-production efforts are frequently slowed by restrictive export control regimes, technology transfer anxieties, and differing industrial standards that take years to harmonize. From a macroeconomic perspective, the rising cost of missile defense is forcing a structural reassessment of national defense budgeting across the Western world. When the cost of defending national sovereignty and critical infrastructure escalates exponentially due to weapon asymmetry, defense spending must consume a larger share of national GDP simply to maintain the status quo. This reality creates severe fiscal friction in democratic societies, where defense spending must compete against rising domestic expenditures, healthcare costs, and debt service obligations. The debate over defense funding is no longer just about buying new platforms, but about sustaining the massive hidden costs of industrial logistics and ammunition replenishment required to fight a prolonged war of attrition. Ultimately, analyzing the Patriot missile system through an objective, analytical lens reveals that military power cannot be measured solely by the technical superiority of a weapon platform in isolation. True military effectiveness is a function of a nation's total industrial output, the resilience of its supply chains, and the sustainability of its economic models under stress. The MIM-104 Patriot remains an extraordinarily capable and combat-proven system that fulfills its technical requirements with remarkable precision. However, without a fundamental restructuring of the industrial base that supports it, the system represents a fragile shield, one that is highly vulnerable to being systematically ground down by adversaries who understand that in the 21st century, logistics and production volume remain the ultimate arbiters of victory.